What does nothing contain? On the Earth, a single cubic meter of air isn't very much. It's roughly 1,000 lungfuls. And yet compared to the cosmic average, it's one of the densest regions in the universe. The largest creatures to swim through this volume are the bacteria, drifting with the winds and searching for a home, although some spend their entire lives airborne. Joining the bacteria is microscopic detritus, skin, snot and saliva exhaled and expelled from creatures around the world. All the complex molecular arrangements that our human senses reduce to smells. And then there is the air itself, diatomic nitrogen and oxygen, carbon dioxide, water vapor, a host of less common molecules like methane and ozone. But that is still not all. Roughly every second, a cosmic ray passes through that cubic volume, produced by some high-energy process in the distant cosmos, like an exploding star or collapsing black hole. This particle will have sailed unmolested for billions of years, only to meet its final end colliding with some unlucky air molecule. There is also radiation, constant and ubiquitous of wavelengths up and down the electromagnetic spectrum, the visible light from the sun shining above, the infrared heat from the ground below, the stray X-ray and gamma ray coursing in from the wider cosmos, and the sloshing microwave and radio waves carrying messages and signals from one side of the globe to the other. And that's without mentioning the particles that almost never make their presence known, the 1,000 trillion neutrinos, the ever-present dark matter. And so, what would happen if you stripped all of that away? What if we managed to remove every single molecule, atom, particle, and photon of radiation? Could we make absolutely nothing? Not just emptiness, not just a vacuum, but pure nothingness? The journey to discover the answer to this question is a strange one that will take us from simple vacuum pumps to the beginning of the universe, from ancient philosophical ponderings to the bleeding edge of theoretical physics. And this is because the question, can nothing exist, has a twin. Why are we here? The Dextra robot, part of Canada's contribution to the International Space Station, is operated remotely from Earth. Named Dextra because it is dexterous, controllers at the Canadian Space Agency's headquarters in Quebec can guide its two multi-jointed arms using live video, eliminating the need for spacewalks and allowing the astronauts a bit of time off. Sometimes it's useful to be able to control something remotely, even from the other side of the world. And if you're looking to remotely control your computer for personal or business reasons, AnyDesk can help. AnyDesk is a lightning-fast remote access tool that makes it feel as if you're sitting right in front of the remote machine. We find it especially useful for video editing. Our editors can access their high-performance desktops back at home, wherever they are. AnyDesk's proprietary codec technology ensures minimal lag and crisp visuals, even over slow or unstable internet connections. This allows us to keep digging into projects, even when traveling abroad or on a relation's rural Wi-Fi. AnyDesk is available across all major platforms, is backwards compatible with older operating systems, and has 99.98% uptime reliability, so you can depend on being able to use it when you need to. And what's more, personal use is totally free, with tailored plans for team and business environments. So head to anydesk.com to try this premium remote access tool, free of charge. The year is 1654, and Otto von Guericke is gently dabbing the sweat from his brow. Standing before the Emperor of the Holy Roman Empire himself, he raises his hand and gives the signal. Everything rests on this moment. There is a loud whinnying, and dust billows into the air as his two teams of horses heave into action, pulling in opposite directions and straining the ropes that connect them. The two sets of 8 are evenly matched, and very little progress is made as the struggling beasts strain and sweat, digging their hooves into the dirt. But no matter how hard they struggle, absolutely nothing happens. Otto smiles. It's all going according to plan. Otto von Guericke was the Burgermeister of Magdeburg, a city in what was then the Holy Roman Empire. In addition to his attempts to help his home recover from a brutal sacking 20 years before by Catholic forces, he was also intensely curious about the latest philosophical thinking, including the increasing popularity of the new heliocentric model of the universe, and this was connected to his experiment by a feature of the old geocentric model that had the Earth at its center. In that model, the universe contained no voids. The Earth had instead been surrounded by a nested series of crystalline spheres that carried the objects of the heavens with no gaps between them. Beyond that was heaven itself. Yet in the heliocentric model, the planets themselves were physical bodies that moved through something. And what that something wasn't exactly clear. It wasn't air, otherwise we should all feel the rush of wind as the Earth moved with great speed. And so then, what was it? Could it be nothing? Indeed, the question of whether nothing was even possible, and by extension a vacuum, had long baffled scientists and philosophers. Ancient Greek schools had not managed to reach a consensus. On one side had been the atomists, led by figures such as Democritus, who divided the universe into two basic components: the atoms and the void. The atoms combined in a multitude of ways to make up reality, creating everything from skin and sweat to light and air to emotions and thoughts. The void, however, was pure emptiness, the stage, so to speak, through which the atoms moved, giving the universe its basic foundation. But opposing the atomists was another line of thinking led by none other than Aristotle himself. Aristotle, like his mentor Plato, outright rejected the concept of the void and the vacuum. The vacuum could not be ascertained by the senses. You couldn't smell it, see it, or touch it, and so if you could not encounter something, could it truly exist? And if that argument wasn't enough, air expanded to fill every volume of space and container. If you tried to create a vacuum, air would simply rush in to fill it. In other words, nature abhorred a vacuum. In Muslim and Western traditions, this authoritative voice of Aristotle had echoed throughout the centuries, with the horror vacui, the abhorrence of the vacuum, becoming the accepted wisdom. And so by 1277, as French Bishop Etienne Tempier began his Pope-approved quest to put the mystery to bed once and for all, the very idea of a vacuum seemed an affront to all that is holy. His investigations had been set off by a simple theological debate taking place within the University of Paris. Could God create a vacuum? After all, the Almighty was almighty and was capable of doing anything. But vacuums, nothing, simply could not exist. Could God create something that could not exist? One side argued that God was capable of doing anything, even the logically impossible, with the other countering that argument. God had set the universe in motion, but even he had to play by its rules. And so in response, Tempier had issued a list of condemnations to silence faculty and get them back in line. There was no limit to God's ability, Tempier said, and he could create a vacuum if he wished. Aristotle was wrong, and that was the end of that. At least it would have been, had the faculty not ignored him. The professors, silenced in one line of thinking, ingeniously hatched another question in its place. If it was possible for God to create a vacuum, then perhaps they are permitted to exist. So could we create one for ourselves? And roughly 300 years after Tempier's condemnations, the polymath scientist René Descartes provided the framework for just such a vacuum. Best known for his dictum, "I think, therefore I am," Descartes also invented something taught to every modern schoolchild: the coordinate system, an arrangement of perpendicular axes that can be used to reference position, movement, and extent. A handy mathematical and geometrical tool, the Cartesian coordinate system became the launchpad for physics, creating the foundation for the Newtonian mechanics that would appear half a century later. And it was also the mathematical embodiment of nothing, of empty space. If you removed everything from the universe, then the coordinate system remained. Perhaps the vacuum was possible, after all. And less than 5 years after Descartes' death, physical proof would finally be provided by Otto von Guericke and 16 horses. Otto had suffered through much to be here. In the sack of the city 20 years before, he had lost everything he owned, as almost 90% of the entirety of Magdeburg was razed to the ground, and he would strive for decades to liberate his home from imperial control. But he was also a keen scientist, and perhaps most importantly, a brewer, and had become interested in the pumps used to remove water from barrels. He devised a mechanical system for pumping air out of a sealed chamber, the world's first working vacuum pump, and ever the clever politician had advertised this new invention as a showcase of his recovering city's wealth and ingenuity. And so after sending out the appropriate feelers, he was invited to demonstrate his invention before Emperor Ferdinand III. Otto had taken 2 hemispheres and sealed them together, and then used his invention to remove the air between them. To prove that the spheres held only vacuum between them, he then had the teams of horses pull on the opposite sides. Despite their enormous strength, they could not overcome the pressure of air surrounding the spheres. Clear evidence that there was something less than air, the vacuum, inside. Sadly, despite the impressive demonstration, Otto failed in his quest to liberate Magdeburg. But the experiment itself would have long-lasting consequences. And several decades later, it would be legendary scientist Isaac Newton who would weave together all these disparate strands of thought into a unified whole. He would borrow concepts from the ancient atomists that individual objects move freely. He would take from Aristotle, noting that air always rushes in to fill a void. He would take Descartes' coordinate system and its insistence on the existence of space, and he would take Otto's demonstration of the existence of the vacuum. He took all of that and created a theory for motion, now known as Newtonian mechanics, where objects only accelerate with the impetus of a force. In this theory, there was an entity, space, that existed with absolute dimensions, the stage on which the players played their parts. Within that space, everything moved. There was a force that he called gravity that dictated the motions of all heavenly objects. The planets were surrounded by a vacuum, by a total removal of all the air that was held by gravity to their surfaces, which allowed them to move effortlessly, without friction, without resistance, without slowing down. The vacuum was real, and indeed most of the Newtonian universe was void. But Newton's insights, as brilliant as they were, opened up a new question. Since it was possible to remove everything from a volume of space, leaving only space itself behind, what then was responsible for carrying the force of gravity? How did light get from the sun to the earth? How could these forces possibly be transmitted across vast distances of nothing? Newton shrugged. Indeed, in his treatise, he explicitly left that challenge to future generations, famously stating, "I have not as yet been able to discover the reason for these properties of gravity from phenomena, and I do not feign hypotheses." It would be up to those who came after to finally resolve the question, to finally feign hypotheses. And so now we can return to our cubic meter of air. By Newton's time, it was clear, both from theory and experiment built up over centuries of inquiry, that it was possible to create a vacuum. A box without air, a box without material. But could it really be that simple? Was there anything left behind? There are these two young fish swimming along, and they happen to meet an older fish swimming the other way, who nods at them and says, "Morning, boys, how's the water?" And the two young fish swim on for a bit, and then eventually one of them looks over at the other and goes, "What the hell is water?" In 2005, the iconic author and thinker David Foster Wallace started a commencement speech with this simple story. His intention was to highlight the importance of awareness and mindfulness in the modern world, that our very existence is something we often take for granted. But this aquatic scene also acts as a simple metaphor for an idea that had existed for centuries within physics. The ether, a mysterious background substance that filled the entire universe. And to understand the meaning of this idea and its rise and fall within science, we have to go back to the early 1800s and the sinking of a ship. The HMS Minotaur was the pride of the British fleet. Its crew had sailed through 3 wartime tests, fighting in battles against the forces of Napoleon on the Nile, at Trafalgar and in Copenhagen. But on December the 22nd, 1810, it finally met its match. Caught up in a storm off the Dutch coast, it became separated from its companions. Blinded by the cloud-covered nighttime sky, the ship ran aground. And shortly after, the Minotaur floundered and turned over, succumbing to the sea. All told, 570 sailors lost their lives that fateful morning off the Dutch coast. While Napoleon welcomed the disaster that befell his enemy, he knew well the costs of hidden dangers off the shores of France to his merchant fleet, which was vital in keeping his war of European conquest alive. And so he turned to his corps of engineers and scientists to devise a solution. Lighthouses had been used since antiquity to alert sailors to hidden threats below the waves and mark prominent locations on coastlines. But in the modern era, with hundreds of ships plying the world's oceans, the feeble light of existing designs simply wasn't enough. And so the role of resolving this growing problem had fallen to the young engineer Augustin Jean Fresnel. He would turn out to be the perfect choice. By that time, the scientific prodigy had already conceived of a revolutionary advancement in our understanding of light. Prior to the 1800s, most scientists believed in Newton's corpuscular theory, that light was made of a stream of tiny particles. But Fresnel and his contemporaries were beginning to view light in terms of waves. With a wave theory of light, they could explain diffraction in a way that particles simply couldn't. And armed with this newfound knowledge, Fresnel set to work making a better lighthouse. Within a century, more than 10,000 lighthouses were equipped with his lens, justifiably earning it the name, the invention that saved 1 million ships. But Fresnel's accomplishments weren't just practical, they also rippled through the 19th century in scientific circles. He had conclusively demonstrated that light was a wave. But a wave of what, exactly? If light was a wave, what was waving? The answers would start to come just a couple of decades later, from quite the unlikely source. Many scientific revolutions have their origins in universities. Down the centuries, countless geniuses have come out of Oxford, Cambridge, and further afield, and gone on to use that training to change our understanding of the way the world works. But sometimes someone seems to appear as if from nowhere. Thomas Edison attended school for only a few months, being taught to read and write by his mother. Nikola Tesla never attended university, and even though Charles Darwin did go to Cambridge, he studied theology. And then there is Michael Faraday. Unlike Fresnel and his lighthouses, Faraday was an unlikely scientific revolutionary. The son of a blacksmith, he had no formal training, learning what he knew by reading all the books he could find in his day job as a bookseller. But despite this, he had an unparalleled knack of physical intuition and insight, and what he lacked in rigor, he more than made up for in imagination. Indeed, for that reason, a century later, Einstein would keep a portrait of Faraday on his wall alongside Newton. And so, from humble beginnings, Michael Faraday introduced something altogether new to the world, and in doing so, would totally change our understanding of the idea of nothing. Faraday was part of an international group of scientists who were just beginning to unlock the mysteries of the electric and magnetic forces. The Frenchman, Auguste Coulomb, discovered that two charged spheres attracted or repelled each other. The Italian, Alessandro Volta, found that he could store and discharge electric energy. The American, Benjamin Franklin, uncovered the true identity of lightning, proving that it was the same sort of electricity appearing in some animals and laboratories. And most remarkably, Faraday himself, along with others, found a strange connection between electricity and magnetism. Changing electrical currents could create a magnetic field, and the movement of a bar magnet through a coil could induce a current. But these new discoveries opened up a host of troubling questions, echoing those of Newton centuries before, to which he never dared propose a hypothesis. How did gravity and electricity and magnetism transmit themselves? If there truly was a vacuum between two electric charges, how did they feel each other's electric force? And this was where Faraday came up with something totally new. It was not a force, or a wave, or a particle, or even a phenomenon. It was an idea. The field. Faraday imagined that a solitary electric charge was not alone. Instead, it was surrounded by an invisible, indelible field, lines of force emanating from the charge. And alongside the electric lines of force were the magnetic ones. Indeed, if you take a bar magnet and sprinkle iron filings around it, you can see these lines for yourself, punching from the north end of the magnet before curving back around to the south end. But to Faraday, these lines weren't just imaginary objects to help visualize the forces. They were physical objects in and of themselves. And the mathematical expression for these lines is the field. In simple terms, a field is a mathematical entity that has values at every point in space. If you look at a map of the weekend weather forecast, you're looking at a field. In the case of electricity and magnetism, however, the field must be more complex, describing not just magnitude, but also direction, like a wind map of an approaching storm. Others, however, bolt to this suggestion at the thought that something could exist, the fields of electricity and magnetism, in the vacuum of space. And this included one James Clerk Maxwell, a Scottish mathematician and physicist. But then Maxwell would have his own revelations, and would not only come to accept Faraday's genius, but embrace it. What's the go of that? In later years, it would be said that as a child, James Clerk Maxwell would be heard to utter this phrase whenever he found something he didn't understand, following it up with a slightly more intense, "What's the particular go of that?" And this intense curiosity would follow him into adulthood. Indeed, Maxwell's motivations as a scientist were simple. When he encountered a new problem, he couldn't relax until the problem was solved. And so it would be Maxwell, this insatiably curious Scot, who would take the baton from Faraday and further revolutionize our understanding of the world. Indeed, it was not only Faraday and Newton that Einstein gave pride of place on his wall. Maxwell was the third and final image. He was the great unifier of physics, realizing that electricity and magnetism were actually two sides of the same coin. He saw that there was in reality only one force, electromagnetism, that manifested in different ways depending on the circumstances. And Maxwell took these new tools, a set of what would become just 4 equations that neatly summarized an entire century's worth of scientific progress, and discovered that the combined field the electromagnetic field could support waves of alternating electricity and magnetism. Having done this, it was a simple enough calculation to find the speed of those electromagnetic waves, and it was in that moment that he encountered something truly remarkable. The speed of those electromagnetic waves was identical to the speed of light. Maxwell had found light itself within his equations. Light was an electromagnetic wave. 3 disparate properties of the universe: light, electricity, and magnetism. They were all so different from each other that for millennia we'd assumed that they were simply unrelated phenomena. Yet Maxwell, employing Faraday's fields to their fullest possible extent, found that they were all, fundamentally, the same. And yet despite the power of this approach, Maxwell did not fully accept all of Faraday's reasoning, for he did not think that lines of force could leap across the vacuum of space unsupported. Instead, Maxwell's insights revived a much older idea. And it is here we must return to the ether. The ether as a concept stretched back into antiquity, believed by the ancients to be the quintessence, the fifth element, the purest possible rarefied air that only the gods themselves could breathe. And as scientific astronomy and cosmology came to the fore, there were various attempts to fill the vacuum of space beyond the confines of the Earth with this ether, this substance that was lighter than air and allowed for the free movements of the planets. However, after Otto and Descartes' discoveries, ether theories started to dwindle in popularity. Perhaps nature did not abhor a vacuum, after all. But with Maxwell's revelations, the ether came roaring back to prominence, this time as the medium through which electromagnetic waves, and therefore light, could propagate. After all, sound waves travel through air, ocean waves travel through water. Electromagnetic waves couldn't simply travel through vacuum. If you emptied out everything from a volume of space, there had to be something left. And so 2 American scientists set out to find it. In the late 1880s, Albert Michelson and Edward Morley created what is now known, rather unimaginatively, as the Michelson-Morley experiment. Like most famous science experiments, the idea behind it was simple, but the execution had to be perfect. They developed a device to measure the speed of light in various directions. Michelson and Morley carefully set up the experiment so that the straight-on beam lined up with the direction of the Earth's motion around the Sun. The light travelling in that direction would be boosted by the speed of the Earth. Light travelling in the other direction would not receive such a boost and would be more sluggish as a result. The logic was that over the course of a year, Michelson and Morley should measure variations in the speed of light. And to put it simply, they did not. It was perhaps the most famous null result in all of physics. The speed of light stayed constant. There was no sign whatsoever of the ether. Within only a few years of their experiment, the ether hypothesis simply faded away. And soon after, Albert Einstein would reconcile the constancy of the speed of light, the lack of evidence for the ether, and Maxwell's equations by revolutionizing Newton's concepts of time and space with his special theory of relativity. There was no background to the universe, he said, no absolute space and time. So over half a century after Faraday had opened the question up again, it looked like space was well and truly empty. Light, radiation, electricity, and magnetism could all be transmitted across the vacuum, the void, without requiring any medium. No matter, no ether, no lines of force, nothing. Outer space was nothing but vacuum, and voids weren't just possible, they were the rule, and that seemed to be the end of it. But of course, it wasn't. For alongside Einstein and his relativistic revolution came another upheaval. Quantum physics was ascending, and it would have much to say about the nature of the vacuum, the nature of nothing itself. But before we enter into that brave new world, let us revisit our box. It seems both emptier and more crowded than before. We've successfully created a vacuum, removing all the particles and radiation from it. We've also removed the ether, the substance that physicists once believed filled up the vacuum of space. Yet the addition of electromagnetic waves and fields muddy the picture somewhat. And so, is there anything left to remove? Or is this the end of the story? You can probably guess the answer to that. History is littered with estimates that turned out to be a little off. By the 1400s, astronomers and mapmakers were well aware that the Earth was round, but what they didn't know was its precise circumference. The best early guess had come in the 2nd century, when Ptolemy had used an underestimate of the distance between Rhodes and Alexandria to arrive at a circumference of 180,000 stadia. But with more correct estimates coming later, Europeans eventually largely agreed that Ptolemy was wrong, and that the Earth was larger. Except for Christopher Columbus. He believed that Ptolemy's calculations were correct, and that it would be feasible to cross the Atlantic Ocean and reach Asia in just a few months' span. He was, of course, wrong, and if it weren't for the Americas, he and his crew would have died in the middle of the ocean. That fateful voyage rested on a miscalculation of roughly 25% and had Earth-changing consequences. But that is nothing compared to the greatest discrepancy in science, one with possibly even greater ramifications, especially for our understanding of the concept of nothing. A theoretical estimate hundreds of trillions of times larger than its measured value. And the origins of that miscalculation lie with the early 20th century British physicist Paul Dirac. Dirac's special genius can be neatly expressed in a quote by someone who knew him well, J. Robert Oppenheimer, father of the atomic bomb. Oppenheimer was writing a letter of recommendation for a talented colleague, and he wrote, simply, "He is a second Dirac, only this time human." Indeed, Dirac was known for two things: his intimidating intellect and his deep introversion. Like Maxwell a generation before him, Dirac accomplished what few physicists could. He unified. Maxwell had brought together electricity and magnetism, and in doing so had discovered the physical basis for light. But Dirac did something even more fundamental. He brought together quantum mechanics and special relativity, and in doing so, he discovered that there was more to the vacuum than we could ever have imagined. In his calculations, Dirac had seen something strange: two complementary solutions. One solution was the world of the familiar, describing the behavior of known particles like the electron. But the other solution contained particles exactly like them, yet with opposite charges. He saw in his equations that interactions could produce equal amounts of matter and this new antimatter. To Dirac, this conjured the image of a vast and infinitely deep sea of matter, one that all of normal physics sat on top of. When you emptied out a box of all its contents, Dirac imagined, you would be left with this invisible sea. This matter would not normally be visible because it had states of negative energy, but occasionally a process could pluck one of those bits of matter out of the negative ocean and give it positive energy. Today, however, most physicists don't view the universe exactly through the lens of Dirac's sea of negative energy particles, although the basic picture does remain, with a twist. Things on a very small scale behave like nothing that you have any direct experience about. They do not behave like waves, they do not behave like particles, they do not behave like clouds or billiard balls or weights on springs or like anything that you have ever seen. So said Richard Feynman in 1965 at the beginning of one of his famous lectures on quantum mechanics. And indeed, by the 1960s, physicists, including Feynman himself, had ascertained something very important. Particles were indeed much different than previously thought. For as quantum physics advanced, it turned out that particles could appear and disappear at will if there was sufficient energy involved. But where did these particles come from? And where did they go? There was only one answer: the fields. In quantum field theory, the modern incarnation of Dirac's original forays into unification, particles are not fundamental entities at all. Instead, the fields have primary physical importance. There is one field for every kind of particle. The photon has a very well-known field, the field first identified by Michael Faraday and honed to perfection with Maxwell's work, the electromagnetic field. And that field is joined by others, one for the electron, one for the top quark, one for each neutrino, and so on. Indeed, in the current standard model, there are 17 in total, though there may be more. These fields fill all of space and time, overlapping one another like oil and vinegar soaked in the same piece of crusty bread. When portions of the field vibrate and excite to higher energy levels and start to travel, we recognize it as a particle appearing as if from nowhere. And when the same patch of field loses energy, the particle seems to disappear. Particles appear to transform into one another because the fields can vibrate and energize each other. When one field vibrates another, it looks to us as if one particle has disappeared and another has taken its place. It was a sea, just like Dirac had supposed, but rather than a sea of particles, it was a sea of fields. And importantly, for our understanding of nothing, the fields are never quite calm. They are always, constantly, incessantly vibrating, just not at the level for us to perceive as a particle. In its original conception, space-time was an empty stage, a blank canvas for all the actors of the universe to play their parts. But when united with quantum mechanics, something comes alive. Any place where you have space-time, anywhere that is, has quantum fields. And so nothing is ever truly vacuum, because the vacuum itself is now imbued with a ground-state energy that cannot be reduced. If you remove all the particles and radiation from a box, you've only eliminated the most energetic vibrations. Countless more remain. The quantum fields that make up the most basic unit of physical reality. And it's not just a little bit of quantum fields, a tiny amount of energy hiding in the background vacuum of the universe. It is infinite. Strictly speaking, by a full measure of the quantum fields, there are an infinite number of vibrations at all scales embedded within them. But perhaps most importantly, in physics, only relative differences matter. If you drop a plate, for example, what matters is the distance to the kitchen floor at your feet, not the height of your apartment off the ground or your elevation from sea level. And so all particle interactions happen on top of this infinite sea of vibrations, just as Dirac imagined it. And this means that as long as we are extremely careful with our calculations, we can still make useful predictions with quantum field theory. At least, that was the idea. Because on the other hand, maybe it's not infinite, and we've been getting it all wrong. Very, very wrong. The most incorrect anyone has ever been. In the late 1990s, two teams of astronomers set out to measure a critical property of the universe: its rate of deceleration. The cosmos has been expanding from the Big Bang for billions of years, but the gravitational attraction of all of its matter, the combined weight of all the stars and galaxies, should slow down that expansion. Measure the deceleration, the logic was, and the astronomers believed that they could get a handle on measuring the total matter contents of the universe. The Supernova Cosmology Project, led by Sol Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Adam Rice of the Space Telescope Science Institute and Brian Schmidt of the Australian National University, got to work measuring the brightness of distant Type 1a supernova, using them as reliable gauges of the expansion history of the universe. And for the first time, they provided a precise measurement of the weight of nothing. To their surprise, they were able to measure a change in the expansion of the universe, but in the wrong direction. They saw acceleration, not deceleration. When Brian Schmidt tells the story of their discovery, he often shares the tale that his team stared at their results in shock. Some were excited, others were in disbelief, and still others felt that we had a long way to go. While I shared in the skepticism, I also felt that it would be wrong not to publish a result just because we did not like it. Yet after months of effort, the data refused to budge, and so they sent a nervous and furtive email to their counterparts. Are you seeing what we're seeing? Indeed they were, and it was the first evidence for dark energy, a mysterious substance that appears to be tearing the cosmos apart at the seams. And the simplest explanation for dark energy is that it's due to the effects of all the quantum fields. In essence, at supergalactic scales, the vibrating quantum fields actually produce an anti-gravitational effect. And this means, by measuring this rate of universal acceleration, we can calculate how much energy is contained in the vacuum. We can use the entire universe to measure the weight of the subatomic. And that is not all, because we can then compare this value to expectations from theoretical calculations. While the vacuum might contain an infinite amount of energy, you can use simple physical rules to cut short the runaway infinities, producing a large but finite result. And it is here where the problem lies. It is here we find the most incorrect answer in all of physics. The results between the theoretical calculations of the vacuum and the observed measured value from the acceleration of the universe differ by more than 120 orders of magnitude. Indeed, by measuring the speed of the acceleration of the universe, it turns out that there isn't that much energy in the vacuum at all, roughly the equivalent of the mass energy of a single proton in every cubic meter of space. And yet, even that enormous discrepancy, is not the biggest issue. The bigger problem is that whatever its measured value is, it is clearly not zero. There is a fundamental entity, the field, in the vacuum, and it has a fundamental energy. The natural amount of energy in the vacuum is infinity, and so, in a way, it's not hard to envision a process that suppresses and cancels out that infinite energy. But it's much, much harder to make that energy reach nearly zero, but not exactly so. The vacuum has a tiny amount of energy, and we don't know why. And so, to return to our core mission, are we now any closer to nothing? We've taken everything out of the box. There is now nothing inside it left, somehow not even the quantum fields. But what if we were to remove the box itself, to make it so that nothing, not even the properties of the universe that allow for boxes to exist, is there? The constants of nature, like the speed of light or the strength of the energy of the vacuum, that oddly tiny non-zero number, appear to be fundamental to the inner workings of the universe. Indeed, they are a part of reality itself. If you were to empty a box of all its contents, the constants of nature would still be there, ready and waiting to refill the box anew if the right conditions were met. So if our mission is to truly achieve nothing, truly remove everything in the universe, could it be possible to eliminate not just material objects and exotic quantum fields, but the constants of nature themselves? Can nothing, true nothing, exist? Science and religion have often gone hand in hand, and men of the cloth have often contributed to scientific advance. Copernicus held a doctorate in Catholic canon law and launched the scientific revolution. Gregor Mendel was an Augustinian friar who kick-started the modern study of genetics by breeding pea plants and observing the results. And Angelo Secchi was an Italian priest who was one of the first to conclusively state the sun was a star. And yet, the young Georges Lemaitre hadn't always intended to become a priest. He'd been a soldier in World War I, but the story goes that the artillery manual for the Belgian army had a mathematical mistake in one of its instructions. He'd pointed out the error to his superior officer, who didn't appreciate the correction. Lemaitre was marked for insubordination, putting a stop to his ambitions to advance within the armed forces. And so it would be after the war he turned to religion, joining a seminary, and perhaps it was his religious education that allowed Lemaitre to see something truly special hidden within the equations of Einstein's general relativity. In 1927, Lemaitre found, just like Einstein did, that relativity naturally predicted a changing, evolving universe. But while Einstein had rejected that conclusion, inserting a cosmological constant into the equations to maintain balance, Lemaitre let the equations simply be, and he argued that we lived in an expanding universe. 2 years later, Hubble would observe the recessional velocity of galaxies, confirming Lemaitre's prediction. But what did it mean to live in an expanding universe? Lemaitre had an answer: the primeval atom, a state of incredible density and energy from which the universe emerged long ago, the precursor to the Big Bang. However, most of Lemaitre's colleagues disparaged his results, considering the idea a bit too close to the biblical story of Genesis. The physicist Sir Arthur Eddington stating blankly, "The notion of a beginning of the present order of nature is repugnant to me," and Einstein himself referred to Lemaitre's physics as atrocious. But in time, the evidence would win the day, and Einstein would become one of Lemaitre's biggest champions. Prior to the development of the Big Bang theory, the universe had a simple story. It existed, it was, it forever would be. But the Big Bang, Lemaitre's primeval atom, had a challenge. In an expanding universe, the cosmos has a finite age. It has a birthday. It has a creation. But it isn't really a beginning. It is simply the opening story of this chapter of the universe, and it's a story not fully told. We can calculate there's been roughly 13.8 billion years since the Big Bang singularity, a finite amount of time, but our mathematics breaks down in the primeval atom at the singularity itself, producing irreconcilable infinities that no known trick of mathematics can circumvent. And so it's natural to ask, where did the singularity come from? Let's return to our box. We've removed all the particles, both visible and dark. We've removed all the radiation. Indeed, let's suppose we take it further and we are somehow able to eliminate even the quantum fields from the vacuum itself. What remains? Is this nothing? In the language of general relativity, the box still isn't empty. That's because there is still space-time, the stage. Space-time is a dynamic entity in its own right, imbued with as much physical meaning and significance as any planet or particle. In an idea going all the way back to Descartes and his coordinate system, space remains, even in an empty volume. And hence, in that volume, there is still something, rather than nothing. But the Big Bang is the origination point for everything, for the entire universe. Space itself has a start at the primeval atom. And so before that singularity, did space even exist? The answer to this question currently resides outside of known physics and in the realm of quantum gravity. though there have been some brave ventures into this unknown land. Eternal inflation, the multiverse, the Big Bounce, conformal cyclic cosmology, no boundary proposals. But though these theories may explain the origins of the Big Bang, they do not explain why the Big Bang, the universe, is the way it is. If you take a box and eliminate everything, even the very identities of space and time itself, there is still physics. In particular, there appear to be fundamental constants of nature that defy explanation and origin. Specific numbers that can only be measured, properties of the universe that we cannot explain through physics itself. We must go out and measure these properties, then incorporate them into our theories. Some of these constants are very familiar, like the speed of light. That speed simply is. It's just how fast light travels in a vacuum. We have no way of predicting that value or deriving it from some more fundamental theory. Yes, in 1865, Maxwell discovered the speed of electromagnetic waves, but that was by combining two other constants, the permittivity and permeability of free space, which gives a measure of how easily electric and magnetic forces propagate through vacuum. And the same holds true for the gravitational constant. Gravity has a certain strength, full stop. Other constants detail the subatomic interactions that govern the quantum world, such as the rest masses of the various particles and the strengths of their force couplings to each other. And of course, the amount of dark energy is another such constant. The vacuum has a certain amount of energy to it, very small but not zero, and we have no mechanism for predicting it. If many of these values changed even by a small amount, life as we know it would be impossible. Our universe would be entirely unrecognizable. And so how and why is this the case? As with many deep issues in cosmology and advanced physics, the answer may lie in some form of multiverse. Perhaps different Big Bangs get different values for these constants, and perhaps even different physical laws altogether. We just happen to be inside this universe because this universe is the only kind that can make us possible. But all of these attempts to explain the values of the physical constants contain a fatal philosophical flaw. They don't solve the problem, they only move the goalposts. They may explain why the constants have a particular value, but they don't explain why the constants exist in the first place. There is always some set of laws of physics that explains how our universe came to be, but there is never any explanation for the laws of physics themselves. This is true even in the case of the multiverse or the string theory landscape, which contrive through some process to generate our familiar laws of physics and properties of the universe. Of course, that process itself must obey some other law, one not yet known to us, to govern its behavior and evolution. And those theories cannot explain themselves either. And so it goes on and on and on. If string theory is true, then why are there exactly this many dimensions? Why are there strings? If eternal inflation is correct, then what created the inflation fields? If the universe had a creator, who created the creator? Indeed, even in the most extreme physical idea you can take, that our universe was born from total nothingness, in a burst of some unfathomable quantum machination, you must explain the existence of the quantum laws that could produce such a process in the first place. For example, in 1973, physicist Edward Tryon wrote a paper speculating that the entire universe may simply be a subatomic quantum fluctuation blown up to spectacular scales. That if the universe had an overall zero energy, it could simply be a temporary borrowing of energy from the quantum foam. But where and why, he couldn't answer. I offer the modest proposal that our universe is simply one of those things which happen from time to time. Indeed, in a review of Lawrence Krauss's 2012 book, A Universe from Nothing, which speculated something similar, the physicist and professor of philosophy David Albert summed up the problem. The fact that particles can pop in and out of existence over time, as those fields rearrange themselves, is not a whit more mysterious than the fact that fists can pop in and out of existence over time as my fingers rearrange themselves. None of these poppings amount to anything even remotely in the neighborhood of a creation from nothing. And so absolute nothingness is not just the creation of a vacuum, as Aristotle railed against and Otto von Guericke demonstrated. It is not in the lack of the ether, which James Clerk Maxwell held on to so he could preserve the propagation of electromagnetic waves, and Michelson and Morley found no evidence to support. It is not in the taming of the roiling quantum fields first envisioned by the mathematically untrained Michael Faraday and given new life by the mathematical giant of Paul Dirac. It is not in the evisceration of space and time itself, an entity created by René Descartes and given a birth in the Big Bang by Georges Lemaitre. Absolute nothingness is the complete and utter destruction of physical laws, of the constants of nature, of reality itself. What would it mean if everything, literally everything, even the underpinnings of reality, ceased to exist? What if we took our box and erased the ability to create boxes, to have anything at all? Is that possible? Perhaps it is. Perhaps there is a state of non-existence so total and complete that even the term state doesn't make sense, an aspect of unreality that our feeble minds cannot yet grasp, as our experiences are too far rooted in the sensory world. But if that were possible, then we must return to the arguments of Aristotle. If we cannot measure it, study it, ascertain it, or even comprehend it, then absolute nothingness cannot exist, because it goes against the very definition of existence. And so in a debate that began over 2,000 years ago in ancient Greece, we are forced to ask again and again and again, can nothing exist? You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.